Good afternoon, everyone. How are you guys doing? That is good. So, yesterday we ended the lecture with the HR diagram. Hi, guys. Happy with the HR diagram? Anything I need to explain? How would we ask about this? So, with the HR diagram, the only thing I would ask you, for example, is where is white dwarfs located, or where is giants located, or where is supergiants located, or where is red dwarfs located? And then the second thing is, why did I call it a sequence in the first place? Because it is a sequence. So as we will learn in a later in this lecture and in the following lecture, when we have a star, when it's a star, as we put it in quotation marks, when they are born, the star will start its life somewhere on this main sequence. And as the star goes through its life cycle, it will move positions up and down this main sequence. But 90% of all stars is in this sequence. So that is why it is a sequence. And then a recap. So what this graph shows is temperature on the x-axis versus luminosity on the y-axis of all stars. So that means the further you go to the right on the x-axis, the cooler a star is. If you go on the left, the warmer the star is. If you go up on the y-axis, the more luminous it is, and if you go down, the less luminous it is. So white dwarfs are extremely small, but they are also very luminous. So that is why they are here. So here you can also see radius in terms of solar radii. Red dwarfs is extremely cool and it's not very luminous. That's what on the right-hand corner. If we go to the giants, they are very cool, but very large. That is why they are very luminous. Same with our supergiants. They are extremely luminous, and some of them can be cooler, some of them can be warmer, but their luminosity will be bigger. So is the size of the star considered in this sequence? Yes. So supergiants are much bigger than giants. So the difference between supergiants and white dwarfs are a couple of million times in mass size magnitude. So that is why this is an important diagram, because from this diagram, you know what the star's luminosity is, its temperature, and its size. And here on the top, it also shows you the classification of how warm it is. So OBAF, so O be a fine girl, kiss me, O be a fine guy, kiss me, the rhyme we learned yesterday. It fits into this. Does that answer everybody's questions? So the further up the vertical axis, the bigger the mass of the star. Yes. Awesome. So we've done now the temperature classification, but we also now have luminosity spectral classifications. And the spectra of stars contain clues not only about their temperature and composition, you can also use a star spectrum to determine whether it is a main sequence star, a giant, or a supergiant. The larger a star is, the less dense its atmosphere, and that affects the widths of the spectral lines. Atoms collide often in a dense gas. Their energy levels become distorted and their spectral lines are broadened. And therefore we can explain it with the hydrogen-Balmer lines. So in this image, these model spectra show how the widths of spectral lines reveal the star's luminosity class. So here we can see when you have a supergiant on top, these lines are not very broad. A giant, they become much broader. And when we have a main sequence star, that is even more broader. So from that, we can say that you look at a star spectrum, you can determine how big it is. And the size categories are derived from spectra are called the luminosity classes because the size of the star is a dominating factor in determining luminosity. Supergiants, for example, are very luminous because they are very large. The luminosity classes are represented by the Roman numerals I for 1 supergiants through V for 5 for main sequence stars, with the supergiants further subdivided into type 1a, 1b as follows. So when we divide it into our classes, we have a type 1a, which is a luminous supergiant. 1b is supergiant, type 2 is a luminous giant, type 3 a giant, type 4 a subgiant, and type 5 a main sequence. So this is something I can ask in the semester test and the exam. And that is, what are the luminosity spectral classifications for stars? You guys happy with this explanation? Awesome. So astronomers can measure the stellar parallax of nearby stars, but most stars are too distant to have measurable parallaxes. These distances can be estimated from the star's spectral type, luminosity class, and apparent magnitude in a process called spectroscopic. Spectroscopic parallax is potentially confusing term because it does not involve an actual measurement of parallax shifts, but it is a method to tell you the distance to the star. Spectroscopic parallax relies on the location of the star in the HR diagram. If you record the spectrum of a star, you can determine its spectral class, and that tells you its horizontal location in the HR diagram. You can also determine its luminosity class by looking at the widths of its spectral lines, and that allows you to estimate the star's vertical location in the diagram. Once you plot the point that represents the star in the HR diagram, you can read off its absolute magnitude. For example, famous star Betelgeuse has an apparent magnitude of about plus 0.4. It is classified as an M2 star 1b. So you can find Betelgeuse plotted in figure 18.11 at an absolute magnitude of minus 6. And the difference between Betelgeuse's apparent and absolute magnitudes is therefore 0 plus 4 minus 0 minus 6, or 6.4. So it's distance calculated from a magnitude distance formula. So reasoning with numbers 8.2 is about 190 parsecs. A combination of parallax measurements made by the Hipparcos satellite and radio telescopes yields a distance of 197 parsecs with an uncertainty of 24%. So the results derived from the spectroscopic parallax method is not too bad. Obviously, a real measurement of the parallax is better, but for distant stars, spectroscopic parallax is often the only way to find their distances. So another cool thing, have you guys heard about binary stars? To help us explain this a little bit better before we continue on, I'm going to show you a quick video.
We have one star in the solar system, the Sun. Sure, it has a lot of planets, moons, asteroids, and comets it schleps with it as it moves through space, but no other star is part of our family. The Sun is alone. Based on that, you might naturally think that, like the Sun, stars are single too. They sure look that way by eye. But when you point a telescope at the sky, you find that this is not the case. A lot of stars travel the universe with companions, and sometimes more than one. With so many stars in the sky, some appear close together just by coincidence, even though in space they're actually very far apart. We call these optical double stars. By the 18th century, astronomers were starting to recognize that many stars that appeared close together really were physically orbiting each other. We call these binary stars to distinguish them from the coincidentally close together double stars. Although the numbers are a little bit uncertain, something like a third to half of all stars in the sky are part of a binary or multiple star system. One such binary system is visible to the naked eye and has been known for thousands of years. You may have seen it yourself. The star marking the kink in the handle of the Big Dipper is actually two stars, one called Mizar and a fainter one called Alcor. They're close enough together that you need decent eyesight to separate them, and they were actually used as an eye test in ancient times. Binary stars almost certainly formed together, near each other in the gas cloud that was their original stellar nursery. Instead of a single clump collapsing and forming a star like our Sun, there are two such dense lumps, and they both collect material until they become true stars. There are lots of different kinds of binary stars. If the two stars can be seen separately using a telescope, they're called a visual binary. This is kind of a fluid classification. As telescopes get better, stars that are closer together can be resolved. These kinds of stars are fairly common. The brightest star in the night sky, Sirius, is a visual binary. It's a luminous blue star about twice the mass of the Sun, orbited by a smaller, much fainter white dwarf. It's funny, too. As I mentioned in an earlier episode, white dwarfs can be very hot and energetic and emit light than normal stars. When you observe Sirius with an X-ray telescope, the white dwarf is by far the brighter of the two. Visual binaries are important because if you observe them long enough, you might be able to see their orbital motion. If we can measure their distance from Earth, then the actual size and shape of their orbits can be determined, and in turn, using the math and physics of gravity, this can be used to find the masses of the stars. In fact, the only way we know to get accurate measurements of stellar masses is when they're in binaries. And once we know the masses of the stars, as we saw in episode 26, we can learn everything else about them, how big they are, how brightly they shine, and even how long they live. It's no exaggeration to say that observing binary stars opened up the new scientific field of astrophysics, applying physics to astronomy. And that led to us understanding everything we do about the universe today. Not bad. Not all binaries are visual binaries, though. Some stars orbit so closely together that we can't split them even with our biggest telescopes. So how do we know they're binary?
Spectroscopy.
As the two stars orbit each other, over time, one will appear to be heading toward us while the other circles away, and vice versa as they switch sides. While we may not see that motion directly, if we take spectra of their light, breaking it up into individual narrow colors, we can see the Doppler shift in their spectra. On their merry-go-round path, one undergoes a red shift as it moves away, and the other has a blue shift as it moves toward us. These kinds of stars are called spectroscopic binaries. Remember Mizar and Alcor, the Big Dipper eye test stars? I said they were a binary system, but I lied. Well, I understated. In even a small telescope, you can see that Mizar is actually a visual binary. But it turns out that both of those two stars making up Mizar are actually spectroscopic binaries too. Mizar is a binary star. Even better, Alcor is a spectroscopic binary too. Since Mizar and Alcor orbit each other, it turns out they make up a sextuple star system. 6 stars, all gravitationally bound to one another. Obviously, stars can be in bigger groups than binaries. There are triple star systems, quadruple, and more. Polaris, the North Star, is actually a pentuple system composed of 5 stars. It's possible lots of stars are born in multiple systems. However, it's pretty hard to get a stable system like that. If the orbits aren't just right, some of the stars will tend to get ejected from the system. What we see today are the ones that coincidentally got things just right. Even then, they may not be stable in the long run. Was the sun born in such a multiple system? We don't really know. It's certainly possible, and one way to find out would be to look for stars that have a very similar elemental composition as the sun. But the sun was born billions of years ago. Plenty of time for any stars born with it to wander off. Even at relatively slow speeds, 4.5 billion years is a long time, and for all we know, they could be 50,000 light years away and completely invisible to us. If there are long-lost siblings to the sun out there, they may remain lost. Just like planets orbiting the sun, binary star orbits can be short or very long. Some stars, separated by tens or hundreds of billions of kilometers, can take centuries to orbit each other, while some are so close they may only take days. One binary star, the most bizarre I know of, is called 4U 1820-30, and it's composed of a neutron star and a white dwarf. Their gravity is so strong and they're so close together that they orbit each other in 685 seconds, 11.4 minutes, roughly the length of this episode. Like exoplanets, binary star orbits are tipped every which way to our line of sight from Earth. But for some of them, we see their orbits edge on, or very nearly so. For these binaries, that means that every orbit we see each of these stars pass in front of each other, blocking it from our view. We call these eclipsing binaries. Eclipsing binaries are interesting because as one star blocks another, the total light we see from the system dips, just like in a solar eclipse when the moon blocks the sun. Over the course of one orbit, we see two such dips as the first star blocks the second, and then half an orbit later when the second passes in front of the first. If the two stars are similar, say both like the sun, then the two dips look very similar. But if one star is much brighter than the other, then the two dips look very different. The brighter star dominates the total light we see, so when the fainter star goes behind the brighter star, the light hardly drops at all. But when that fainter star blocks the brighter one, we see a bigger dip in the light. By carefully examining the sizes and shapes of the dips this way, a lot of interesting information can be gleaned from the system, including the sizes, masses, rotation rates, temperatures of the stars, the size and shape of the orbit, and even the distance to the system. Some stars, like humans, enjoy cuddling. They get so close together they become contact binaries, literally two stars touching each other. These are very strange objects. The stars can be stretched out into teardrop shapes due to the mutual tidal effects. If they get very close together, they merge into a double-lobed stellar peanut shape, like two stars cocooned in shared material. This can make things really weird for them. Imagine two stars born at the same time, perhaps a few million kilometers apart, tightly orbiting each other. One has, say, 5 times the mass of the sun, so it's a hot blue star, and the other one just 1/2, so it's a red dwarf. The red dwarf doesn't do much. It just slowly fuses hydrogen into helium, glowing feebly. The bigger star, though, goes through its nuclear fuel rapidly and becomes a red giant. It blows off a wind of matter and loses mass. Since the star's gravity depends on their masses, as the big star loses mass, the orbits get a little wonky, becoming more elliptical. But when the massive star swells, it gets so big the two become a contact binary. A lot of the material leaving the higher mass star gets dumped on the red dwarf, which starts to grow. Eventually, the big star loses most of its mass and becomes a white dwarf, while what used to be the lower mass star has grown and now might be more massive than the other star. It's a bit like Robin Hood taking from the rich and giving to the poor. If he gets too enthusiastic about it, then the poor become rich while the rich become poor. When we look at that binary system, we see a white dwarf star that is clearly more evolved than a high mass one, the opposite of what we expect. This is called the Algol paradox after the contact binary star Algol in Perseus, which shows this effect. Mass transfer between two stars can yield even more dramatic results. Imagine this same system a couple of billion years later. The high mass star has lost its outer layers and is a dense white dwarf. The other star eventually runs out of hydrogen fuel and swells into a red giant. This material then flows onto the white dwarf. White dwarfs have cruelly strong gravity. If the hydrogen flowing onto its surface piles up enough, the gravity can squeeze it so hard it fuses into helium. If the flow rate is just right, it piles up on the white dwarf and then undergoes fusion in a single colossal flash, erupting in a huge explosive flare. Some of these explosions can be incredibly violent, tens of thousands of times brighter than the sun. When this happens, a previously invisible star can suddenly flare into visibility in the sky. These have been seen historically and called stellar novae for new star. I love the irony. These stars actually have to be old, near the ends of their lives, to go nova, but the name stuck. The explosion can blow out the stream of matter falling from the other star, but when things settle down after a few weeks or months, the matter stream can fall back on the white dwarf and the whole cycle repeats. These are called recurrent novae. If the matter stream is slower, the material can fuse steadily, never piling up, so it never explodes. However, the mass of the white dwarf still increases. If it reaches a mass of around 1.4 times that of the sun, it gets compressed by its own gravity so much that its temperature soars upwards. It gets so hot that carbon fusion initiates, and that is a big problem. In a normal star, it would just expand due to all the extra energy being generated, but a white dwarf can't. It's ruled by electron degeneracy pressure. The extra energy just goes into fusing more carbon, and what you get is a runaway thermonuclear event. All the carbon everywhere inside the white dwarf fuses all at once. All of it. Basically, a solar mass of carbon will instantly fuse, releasing all that energy all at once. It's like setting fire to a dynamite factory. The star explodes. You get a supernova, and it's a completely different process than what we saw when a high-mass star explodes. But coincidentally, it releases about the same amount of energy. The star tears itself to vapor and gets so bright it can be seen literally most of the way across the universe. Ooh, this makes them very, very important indeed, as you'll see in a future episode. Today you learned double stars are stars that appear to be near each other in the sky.
So that is very, very cool, right? Something that is, see a question now. I will just go to the slides and I will answer the question. So he mentioned how the red star will become bigger than the blue after merging, and the blue becomes smaller. What's the cause when initially the red one is bigger and the blue initially was a smaller one? So that's how it happens when those stars form naturally in their lifetimes. So as they continue on, the one will swell into a giant, and then they will become touching binaries. And then the one will steal matter from the other one. So then the one stealing the matter will become bigger, and the one losing matter will become smaller. Does that answer your question? Awesome. So then I know stars could fuse. So yes, stars can exchange matter from one to the other. And also that's how stars generate energy, through nuclear fusion. So one thing that is also important to note is, before I give you the answer, how common do you think binary stars is or are in the universe? So they are extremely common. So the majority of the stars we can see with our unaided eye are actually binary stars. So when you look at these statistics, 50% of all stars are binary stars. Did you guys know that? So yes, so 50% of all stars we observe are actually binary stars. So it's actually a very, very common phenomena. So as we discussed, here we have a binary pair. So here we can look at brightness. As the one dips in front of the other one, we can see this is a eclipsing binary. So one thing that we can use, and what binary stars are useful for, is to determine the mass of the system. If you determine the mass of the system, you can determine the mass of both individual stars. And if you know what the mass of the individual stars is, you can use that information to determine the mass of other stars. So here is a example where we have the center of mass, both orbits from. So there's a radius of star B around its center point, radius of A, and we can calculate both masses. So question, is it possible that there can be two contact stars that don't steal from each other and still live in equilibrium-like state? Almost. So there are some systems where the two stars or the two contact binaries. So let's say you have star A as the big one, star B as the small one. So what will happen over time is if they're contact binaries, star B will steal matter from star A. So star B becomes the big one and star A becomes the small one. Then at some point, star B will swell up again, becoming a giant, even a supergiant. And then star A will start stealing matter from star B. And that can go on for a couple of billions of years. And there's been some instances where we have been observing stars. And the star being observed we determined is too bright for its age. That means it appears to be a young star, but in fact, it's a very old star. And when you look carefully, you'll see that is a binary system where you have a sort of equilibrium where there's a back and forth between these two stars of matter exchanging, and that extends the lifetime of these two stars quite a lot. Does that answer your question? Awesome. And that will continue on until one of those stars has run out of all of its fuel that can be fused. So yes, the process cannot go on indefinitely, but there will still be a situation where you have almost equilibrium, and that will extend both stars' lives to a couple of billion years extra. So to find the total mass of binary star system, you need to know the sizes of the orbits and the orbital periods. So the length of time the stars take to complete one orbit. The larger the orbital period is, the stronger the star's gravity must be to hold each other in orbit. For example, if two stars whirl rapidly around each other in small orbits, then their gravity must be very strong to prevent their flying away from each other. Such stars would have to be very massive. From the size of orbits and orbital period, you can figure out the masses of the stars, explained in reasoning with numbers 8.4. So here, this is a question I like to answer for the semester test and exam. So let's go through this example. Kepler's third law of orbital motion worked only for the planets in our solar system. And when Isaac Newton realized that a mass produced the gravitational attraction that causes orbits, he made that law into a general principle. Newton's version of Kepler's third law applies to any pair of objects that orbit each other. So the total mass of the two objects is related to the average distance a between them and their orbital period b. If the masses are ma and mb, then we have ma plus mb equals a squared, a to the power 3 divided by p squared. And this formula, a is expressed in AUs, p in years, and m in solar masses. So notice how this formula is related to Kepler's third law of planetary motion. Almost all of the mass of the solar system is in the sun. So if you apply this formula to any other planet in the solar system, the total mass is one solar mass. Then the formula becomes p squared equals a to the power 3. So because we are working with solar mass, what happens is the ma plus mb equals 1. Like I said, the symbol is solar mass. So when you rewrite this equation, so if you look at this equation over there, so let me just clear this, that becomes 1 equals a to the power 3 over p squared. And then if you simplify it, you get this over here. Everybody happy? Awesome. So the majority of examples we are going to use, and specifically for your semester test, you are going to use this form of the equation. So if we look at an example, if you observe a binary system with a period of 32 years, an average separation of 16 AU, what is the total mass? So here, you just plug it into the equation and you can calculate m, the mass. Or you can do the other way around. I can give you the orbital period, or I can give you one of the other variables, and then you have to solve it. So for an example B, let's call the two stars in the previous example star A and star B. And suppose star A is 12 AU from the center of mass, and star B is 4 AU away. What are the individual masses? So then the ratio of the masses must be 12 to 4, which equals a ratio of 3 to 1. What two numbers add up to 4 have the ratio 3 to 1. So star B must be 3 solar masses and star A must be 1 solar mass. So it's just straightforward plug and play formulas. Also, each star in a binary system moves in its own orbit around the system's center of mass, the balance point of the system. So if one star is more massive than its companion, then the more massive star is closer to the center of mass and travels in a smaller orbit, while the lower mass star whips around in a larger orbit. And the ratio of masses of the stars, MA divided by MB, equals the radius of B divided by radius of A, the inverse of the ratio of the radii of the orbits. If one star has an orbit twice as large as a star's orbit, then it must be half as massive. The period and the total size of the two stars' orbits tell you the sum of their masses, and the relative sizes of the two orbits give you the ratio of their masses. That is enough to let you determine the individual masses of each star. Figuring out the masses of the stars of a binary star system has some further complications. The orbits of the two stars may be elliptical, and although the orbits lay in the same plane, the plane can be tipped at an unknown angle to your line of sight. And further distorting the observed shapes of the orbits. So astronomers must find ways to correct for these distortions. In addition, they can estimate the true size of the orbits in astronomical units. Finding the masses of binary stars requires a number of steps to get from what you can observe to what you really want to know, the masses. Although there are many different kinds of binary stars, 3 types are especially useful for determining stellar masses. And these are discussed separately in the next section. So just a heads up, if you write on the slides, everyone can see it. So please don't write on the slides. So the first one is a visual binary system. The two stars are separated visibly in a telescope. Only a pair of stars with large orbits can be separated visually. If the orbits are small, the telescope cannot resolve the star images. And if you see only a single point of light in a visual binary system, you can see each star moving around in its own orbit around a center of mass. Astronomers study visual binary systems by measuring the positions of the two stars over the course of many years to map the orbits. So when we look at Sirius, the brightest star in the sky, that is a visual binary system. You can see that through a pair of binoculars. If we look at Alpha Centauri, the closest star to us, which is 4.2 light years away, that is also a visual binary that you can see with a small telescope, which is very, very cool. So here we can see the bright star Sirius has a faint companion, Sirius B, a white dwarf. So here we can see Sirius A and Sirius B. And over the years, astronomers can watch a few stars move and map their orbits. So a line between the stars always passes through the center of mass of the system. And a star closer to the center mass is the more massive star. So the elliptical orbits are tipped at an angle to our line of sight. So here we can see the center of mass and the two orbits of Sirius A and Sirius B. So visual binary systems are common. More than half of the stars are members of binary star systems, and many of those are visual binaries. However, many of those systems cannot be analyzed completely. For example, famous star Polaris has two stellar companions. One of the stars that orbits Polaris has an orbital period estimated to be over 1,000 years, so the exact size and period are not well known. The other companion is so close to Polaris that it is hardly distinguishable even with the Hubble Space Telescope. So now we've done visual binaries. So the next one is spectroscopic binary systems. If the stars in a binary system are very close together, their telescopes limit by diffraction, and seeing may reveal only a single point of light. By looking at a spectrum, which is formed by light from both stars and contains spectral lines from both, astronomers can sometimes tell that there are two stars present and not one, and such a pair of stars is a spectroscopic binary. Most known binary systems are spectroscopic binaries, and many of the familiar stars in the sky, apparently single stars, are actually two or more stars orbiting one another. So here, for example, is an example of a telescopic binary star system. So in image A, at a bend of the hand of the Big Dipper, lies a pair of stars Mizar and Alcor. So here we can see them, Mizar and Alcor. Through a telescope, you can discover that Mizar has a fainter companion and is so a member of a visual binary system. In adaptive optics, observations reveal a faint close companion of Alcor, not pictured in this diagram. So in image B, the spectra of Mizar sometimes show a single spectral line at the top, and other times show double lines at the bottom, indicating that the main star of the visual binary system is itself a spectroscopic binary system rather than a single star. So when we have a spectroscopic binary, if the one star is moving this way in its orbit, it's receding from us and it's redshifted. And star A in its orbit is moving towards us, so that means it's blue shifted. So now this one becomes more blue shifted, that one becomes more red shifted as they move around in their orbit. And that is how we determine it is a spectroscopic binary. You guys all happy with spectroscopic binaries? Awesome. So the last set is the eclipsing binary systems. So as mentioned earlier, the orbits of two stars in a binary system always lay in a single plane. If that plane is nearly edge on to Earth, then the stars will appear to cross in front of each other. Imagine a model of a binary star system in which a cardboard disk represents the orbital plane and balls represent the stars. If you see the model from the edge, then the balls that represent the stars can move in front of each other as they follow their orbits. Seen from Earth, the two stars are never visible separately, as only a single point of light. But as the stars repeatedly block each other, light from our point of view, the total brightness of the point of light periodically decreases. And such a pair of stars is called an eclipsing binary. So we can imagine it as a cardboard disk with these two balls. So if the one smaller one moves front of the one of the bigger one, you'll see it eclipsing it and the other way around as well. So this animation that we're seeing in the video is an example of an eclipsing binary. So the resulting variation in the brightness of the system is shown as a graph of brightness versus time, or we call that a light curve. The light curve of eclipsing binary systems can be difficult to analyze, but they contain tremendous amounts of information. So the eclipsing binary algol consists of a hot B star and a cooler K star. And the eclipses are partial, meaning that neither star is completely hidden during eclipses. And the orbit here is drawn as the cooler star was stationary. So relative size of the Sun is indicated by the small open circle. So in this image, we can see the observed light curve of the binary star Chappée. Shows that the two stars are so close together that gravity distorts their shapes. And slight variations in the light curve reveal the presence of transient dark spots at specific places on the star's surface. This upper curve shows what a light curve would look like if there were no spots. So now all that we have learned between yesterday and today, we can put together a consensus of stars. So you have luminosities, temperatures, sizes, and masses of stars. And now you can put all those data together to paint a family portrait of the stars. As in any family portrait, both similarities and differences are important clues to the history of the family, as you begin trying to understand how stars are born and how they die. Asks a simple question. What is the average star like? Answering that question is both challenging and illuminating. If you want to know what the average person thinks about a certain subject, you take a survey. If you want to know what the average star is like, you need to survey the stars. Such surveys reveal important relationships among the family of stars. Not many decades ago, surveying large numbers of stars was an exhausting task, but modern computers have changed that. Specially designed telescopes controlled by computers can make millions of observations per night, and high-speed computers can compile these data into easy-to-use databases. Those surveys produce mountains of data that astronomers can mine while searching for relationships with a family of stars. What would you learn about stars from a survey of stars near the Sun? So astronomers have evidence that the Sun is a typical place in the universe. Therefore, such a survey could reveal general characteristics of stars everywhere and might reveal unexpected processes governing the formation and evolution of stars. So when we survey stars, there are three important things to notice. The first is making a good survey is difficult, because you must be sure you get a good sample. If you don't survey enough stars, or if you miss some kind of stars, your survey might produce biased results. Secondly, luminous stars are rare. The most common types of stars are the low luminosity red dwarfs. A careful survey reveals that what you see in the sky is deceptive, and most of the stars in the sky are not typical stars, but instead are highly luminous giants and supergiant stars that can be seen from great distances. If you survey enough stars and plot the data in an HR diagram, you can see the patterns that hint at how stars are born, how they age, and how they die. If you label an HR diagram with the masses of the plotted stars, as in figure 8.20, you'll discover that the main sequence stars are ordered by mass. The most massive main sequence stars are hot and luminous stars. As you run your eye along the main sequence, down to the right in the diagram, you will find successfully lower mass stars until you reach the lowest mass, coolest, lowest luminosity main sequence stars. So here we can see it. So here we can see a star with 18 solar masses, 3, 1.7, 1 solar mass where our own sun is, and 0.1 solar masses. So here we can see our supergiants are 18 solar masses, 12, 10, 16, and we get even higher masses. And here we can see our very low mass stars as well. So stars that do not lie in a main sequence are not in order on an HR diagram according to mass. Giant and supergiant stars are a jumble of different masses, although supergiants tend to be more massive than giants. In contrast, all white dwarfs have about the same mass, somewhere in a narrow range from 0.5 to 1 solar mass. Because of the systematic ordering of mass along the main sequence stars follow a mass-luminosity relation. The more massive a star is, the more luminous it is. Although giants and supergiants follow different mass-luminosity relations and white dwarfs do not follow one at all, the link between mass and luminosity is critical in astronomy. The density of stars reveal another pattern in the HR diagram. The average density of a star is its mass divided by its volume. As you will learn in the next chapter, stars are not uniform in density, but are most dense at their centers and least dense near their surfaces. The center of the sun, for instance, is about 150 times as dense as water, so 15 times denser than lead. Its density near the visible surface is about 3,400 times less dense than Earth's atmosphere at sea level. So the sun's average density is approximately 1 gram per cubic centimeter, about the density of water, an intermediate between its central and surface densities. Main sequence stars have average densities similar to the sun's, but giant stars have low average densities ranging from 0.1 to 0.01 grams per cubic centimeter. And enormous supergiants still have lower densities ranging from 0.001 to 5 zeros and 1 grams per cubic centimeter. The white dwarfs have masses about equal to the sun's, but are very small. Only about the size of Earth. That means that matter is compressed to enormous densities. On Earth, a teaspoonful of this material would weigh more than 5 tons. Density divides stars into 3 groups. Most that are main sequence stars, with densities like the sun. Giants and supergiants are very low density stars, and white dwarfs are high density stars. So here we can see the mass-luminosity relation shows that the more massive a main sequence star is, the more luminous it is. And the open circles represent white dwarfs, which do not obey the relation. And the red line represents the equation L equals m to the power 3.5. So that is what we call the mass-luminosity relation. So that is another question I can ask in the semester destiny exam. So you can estimate the luminosity of a main sequence star based on the star's mass. Main sequence star luminosity in terms of the sun's luminosity equals its mass in solar masses raised to the power 3.5. So this is the mathematical form of the mass-luminosity relation, and that is only approximation as shown by the red line. So an example, what is the luminosity of a main sequence star with 4 times the mass of the sun? So the solution, the star is about 128 times more luminous. So you take the L, you plug the 4 into the M, and you get your answer. So ladies and gentlemen, that was our consensus of stars and how we would discuss our family of stars. Do you have any questions? No questions. So now we can continue with our next set of lecture slides. I'm just uploading the lecture slides. Come on. Just waiting for the lecture slides to upload. Okay, the slides have uploaded, so I'm going to start sharing the slides. Can everyone see the slides? So for this lecture, we are going to discuss the formation and structure of stars. So we're going to look at the interstellar medium, making stars from the interstellar medium, young stellar objects and protostella disks, stellar structures and nuclear fusion, and main sequence stars. So for this lecture, we need to answer 5 fundamental questions. The first one is, how do astronomers study the gas and dust between the stars, called the interstellar medium? Secondly, how do stars form from the interstellar medium? Thirdly, how do stars remain stable? Fourthly, how do stars make energy? And then lastly, why do the luminosities and lifetimes of stars depend on their masses? So stars are not eternal. And when you look at a sky, you see hundreds of points of light. And amazingly enough, each one, like the sun, is a tremendous nuclear fusion reactor held together by its own gravity. So the stars you see tonight are the same stars your parents, grandparents, and great-grandparents saw. Stars don't change perceptibly in a person's lifetime, or even during all of human history, but they do not last forever. So stars are born and stars die. So when I speak about stars, the death of stars, it's not literally the Death Star in Star Wars or a star that exploding, but how do they end? So before I continue with this, I'm going to show you one more video that might explain this a little bit better.
The sky looked pretty, flickering intense diamonds dotting the velvety. I look pretty, flickering intense diamonds dotting the velvety night. But make no mistake, they are churning cauldrons of violence, barely constrained thermonuclear generators, creating enough energy to vaporize the Earth 1,000 times over. Their lives depend on it. Heck, our lives depend on it. But in their case, how they live and how long they live depends on that creation of energy. And in this universe, nothing lasts forever. Very roughly speaking, we can divide stars into 2 groups, low-mass stars and high-mass stars. That line lies around 8 times the mass of the sun, and the reason for that is something we'll get to shortly. Things get very exciting at the high end, but for now, let's take a look at the low-mass end of the scale. Things are simpler there. Stars make energy in their cores by fusing hydrogen into helium. This is actually a pretty complicated process with lots of steps, but in the end, 4 protons plus some other ingredients get turned into one helium nucleus. Each time this happens, a little bit of energy is released, but in the core of a star, it happens countless times every second. It adds up to a lot of energy, enough to power a star, in fact. The rate at which hydrogen fusion occurs depends on how much pressure the star has in its core. A higher mass star squeezes hydrogen harder, so it fuses far more quickly. The rate is so much higher, in fact, that even though they're a lot bigger than low mass stars, high mass stars run out of hydrogen fuel in their cores more quickly. The lower mass a star is, the longer it lives. In the lowest mass stars, cool red dwarfs, the rate is so slow they last a long time. But there's more to it than that. They fuse hydrogen only in their very centers, and their cores aren't very big. Outside of this small region, the gas is convective, which means the hot stuff rises, cools, then falls back to the core. That's important because it means the entire star is available for fuel. Both hydrogen and helium rise up through the star and then fall back down. The star can't fuse the helium, but the hydrogen that makes it back to the center is just more grist for the mill. Even after a long time, these stars can still shine as the hydrogen mixed throughout the star eventually makes it down to the center. So how long can a really low mass red dwarf last? 1 trillion years. 1 trillion! The universe itself is less than 14 billion years old. So even the oldest red dwarf stars are basically infants. They're just barely getting a start in life, and they'll look pretty much the same for the next, 990 billion years or so. Eventually, though, they do run out of fuel. When one does, the star itself will be nearly pure helium, plus whatever heavier elements it was born with, and fusion will cease. It'll then cool, which will take many more billions of years. Finally, it'll be a cold, black, dead star, and for them, that'll be pretty much that. Or so we think. The universe is far too young for any of these red dwarfs to have run out of fuel yet. That's true for stars at the lower end of the mass scale, up to roughly 1/3 of the mass of the sun. But stars with more mass than that, stars more like the sun itself, work a little differently. Their cores are bigger and hotter and denser. The different conditions inside them means the material in them doesn't convect. The hot stuff doesn't rise away from the core. What's in the core stays in the core. Outside the core, there's a very deep and active convection zone, but that doesn't interact with the material in the core itself. This means that not only do stars near the sun's mass use up their fuel more quickly than red dwarfs, they have relatively less fuel to work with as well. Depending on their mass, their lives aren't nearly as long. For the sun, that total lifespan is about 12 billion years, give or take. The sun is nearly 5 billion years old now, so it's approaching middle age. Its life is similar to other stars of similar mass, so let's take a look into the far future. Will our sun go gently into that good night? Ever since the sun was born, it's been fusing hydrogen into helium in its core. The helium is trapped there, unable to be used as fuel, and it's building up in the core like ash in a fireplace. As it does, the density in the sun's core slowly increases. When you compress a gas, it heats up. That means every day the sun's core gets a wee bit hotter. That extra heat works its way out through our star, heating up the outer layers too. A hotter gas shines more brightly, so the sun has been steadily increasing in brightness too. It's an incredibly slow but inexorable process. The sun's increased in luminosity by about 40% since it was born. And it's not done. Helium is still building up in its core, and eventually it'll run out of hydrogen to fuse. Without fuel, fusion in the core will stop. Helium can be fused into carbon and a little bit of oxygen and neon, but it has to be incredibly hot to do so, and the sun's core won't be anywhere near those conditions. Still, half the sun's mass is bearing down on the core, so even though fusion stops, the core will continue to contract and heat up. It'll get so hot that the temperature outside the core will get to hydrogen fusion temperatures. Like igniting a match by holding it near a flame, the hydrogen outside the core will start to fuse. That'll occur in a shell surrounding the core, adding its heat to the outer layers of the sun as well. When you heat a gas, it expands. The sun's outer layers will do just that, and our star will grow to well over twice its current size. Astronomers call a star like this a subgiant. Not only will it grow, but its color will change. The sun will be giving off more total energy than it does now, but its surface area will increase so much that the amount of energy radiated per square centimeter will go down. There'll just be a lot more square centimeters. This means, ironically, that the surface will actually cool. The sun's temperature will go down. Cooler stars are red, and so the sun will be too. But the core still isn't done. The details are complicated, but the core continues to contract and heat up. It gets so hot that the outer layers swell even more, and the sun can bloat up to a fantastic 10 to 150 times its present size. It will then be a red giant. Red giants are fantastically bright because of all the energy percolating up from their interiors, coupled with their enormous size. When it turns into a red giant, the sun will increase its luminosity by an incredible 2,000 times. That huge increase in luminosity does more than just make the sun bright, though. As a red giant, the sun will be so swollen that the gravity at its surface will drop substantially from what it is now. The force of gravity holding it down is weak, but the force from all that light blasting out from below is strong, easily overpowering gravity. Material on the surface will get blown off like a leaf in a hurricane. Think of it as a super solar wind. That means the sun will shed mass a lot faster than it does now. While it's a red giant, it'll lose fully a third of its mass. At some point, the core contracts and heats up so much that the conditions will finally be primed for helium fusion. Suddenly, helium is converted into carbon, releasing a lot of energy. In a weird twist, due to a lot of very complicated physics, the core itself winds up expanding, absorbing most of that energy. In the end, less energy is pumped into the outer layers, so the sun's outer layers contract. The sun shrinks. The outer layers get dense again, which warms them up a bit, and the sun turns from red to orange. It's still pretty big, more than 10 times its current day size, and puts out 20 to 50 times as much energy as it does now. But then we see a sort of reboot of what's happened in the core before. This time, though, helium is fusing in the core, and the carbon is building up like ash. Once again, the core starts to contract and heat up. This dumps more energy into the outer layers, they expand and cool, and the sun turns into a red giant again. This time, it's even brighter and bigger and loses even more mass, shedding over half of what's left. In the meantime, helium fusion isn't very stable, to say the least. It swings wildly, increasing and decreasing its rate by huge amounts on very short timescales. The sun will probably undergo a series of tremendous paroxysms, epic eruptions as the helium fusion spikes, creating huge surges in energy production. It'll lose even more mass each time. Finally, though, we approach the end game. The sun doesn't have enough mass to squeeze carbon atoms enough to fuse them. They build up in the core until there's no more helium and fusion stops. On top of that, well, there's nothing on top of that. By this time, the sun will have literally blown off all its outer layers. It's essentially a naked core, a hot, intensely bright, super compact ball, not much bigger than Earth. We call this a white dwarf. Its fate is sealed. It can't generate energy, so it'll cool and fade over the next few tens of billions of years. At that point, we can safely say the sun is dead. But that's not always the case for all stars. Some with more mass than the sun still go through another phase before dying. They form what are called planetary nebulae, and these are so amazing and beautiful that they rate their own episode, which, along with more fun stuff about white dwarfs, we'll get to next time. So that's it for the sun. But what about us? Of course, the Earth won't fare very well during all this. It'll get cooked before the sun even becomes a subgiant, and by the time the sun is a red giant, we'll be good and fried. The average temperature on our planet will be so high that it'll melt rocks, and in a sense, it'll look much like it once did so many billions of years before, when it first formed, a molten ball of rock. But it gets worse. When the sun expands, it'll reach a radius very close to the size of the Earth's orbit now. Does that mean our planet itself will be consumed by the sun? Maybe not. As the sun expands, remember, it loses mass. That means its gravitational pull will weaken, and Earth will move out from the sun into a bigger orbit. If things work out right for us, the Earth will back off faster than the sun expands, and we'll avoid finding out what it's like to be inside a star. Due to a quirk of physics, if the sun loses more than half its mass, its gravity will decrease so much the planets will no longer be gravitationally bound to it, and they'll be flung into interstellar space. I'm not sure that's any better for us. Either way, the Earth will have been long dead, and hopefully humanity will have figured out the trick to interstellar travel by that time. All those Earth-like exoplanets around younger stars will look pretty nice in a billion years or two. Mind you, this isn't happening anytime soon. The sun won't become a subgiant until it's nearly 11 billion years old, over 6 billion years from now. The first red giant stage happens when it's over 11.5 billion years old, and the second stage a half billion years later. This is a long, long time coming. If the sun had more mass, it could avoid this fate. A star with about 8 times the sun's mass can. It has enough mass to squeeze those carbon nuclei hard enough to fuse them together. Those high mass stars have a much different and far more explosive fate than lower mass stars like the Sun. And trust me, we'll cover that in lots of fun detail soon. And while this all sounds very bleak, not all is lost. This is all part of the natural cycle of the universe. And in fact, we wouldn't be here at all if it weren't for the way stars live and die. Be thankful for what you have, and that we can not only observe it, but understand it too. Today you learned that very low mass stars live a long time, fusing all their hydrogen into helium.
So that is very cool and very insightful. And that will give an indication what we will be talking about in this lecture. So let me put on the lecture slides. I see there's a few questions. So the first one, sir, where is the first question? When the sun gets hotter, is there a chance it'll create the correct conditions for life on other planets further than Earth? Yes, there could be a chance. So there might be a chance that Mars, for example, will now be better suited for life. But the problem with Mars is, even though it will have a better temperature, it doesn't have a magnetic field. That's the problem. When you go look at Jupiter is inhospitable in any case. So yes, on Mars, the temperature will be warmer, but there's other conditions that play into if it can support life or not. I hope that answers your question. So question, how does lithium, magnesium, etc. form, considering that helium fusion creates carbon? Yes, so what we'll learn about, this is what happens in low to medium mass stars. They will end in as a white dwarf and usually stops at carbon. But high mass stars that we will talk about in the following lecture has enough energy and gravitational energy to fuse heavier elements, so they can go past carbon fusion. And then the next question is incorporated into your question. Sir, can a star become a black hole? And if it can, how does that happen and how big must it become a black hole? So what we will learn is high mass stars, at the end of its lifetime, instead of being a naked core, it will blow off its outer layers. And depending on how much mass it has, it will either be a it will either be a neutron star. So then the core is compacted, and when the outer layers are blown off, that will have enough energy to fuse even higher elements. But if you have a very, very massive star, as you think about, we will see the exact figures, but somewhere in a ballpark of about 14 to 15 times more mass than our own sun, then at the end of its lifetime, the core will collapse in on itself, forming a black hole. And then the outer layers forms a supernova explosion. That is where all our rare metals are created, such as lithium, magnesium, iron, gold, silver, nickel. So all of that is created in supernova explosions. And then as our own sun formed and planets, as our sun formed, the planets formed exactly at the same time around the sun. That captured that interstellar dust from supernova explosions, and that is where our rare metals comes from. And then another question, and do nebulas come from the death of stars? Yes, that is where nebulas comes from. So nebulas comes from usually at the end of stars' lifetimes. And what we will learn is new stars then form inside these nebulas. I hope that answers all of your questions. Awesome. So how can you know what the life cycles and internal processes of stars are, given that you won't live long enough to see them evolve, and you can't see inside them? The answer lies in the methods of science. By constructing hypotheses about how nature works, and then testing those hypotheses against evidence from observations, you can unravel some of nature's greatest secrets. When people use the phrase the vacuum of space, they reveal a common misconception that space is empty. But space is not empty. There is gas and dust between the stars, called the interstellar medium, abbreviated ISM. So here in image A, we can see the visual wavelengths. The spaces between the stars and in around the constellation Orion seem empty. But in image B, an infrared image, reveals the swirling clouds of the interstellar medium. The visible Orion, the core of the large Orion star-forming region, that is the brightest white patch at the lower right in the infrared range. So here that we see right here, this circle right here, that is the Orion Nebula. And that is, looking at the left image right here, Orion, center of Orion's belt. And that is my most favorite object to observe. So question, why can't some travel through space if there's gas? Why can't some travel through space if there is gas? Sound. So what I say, why, can you rephrase that question perhaps? So why can't sound travel through space if there is gas? Is that what you... okay, cool. So one thing is, even though there are some gas and dust particles, its density and there's so few of them that is not enough for sound to propagate through. So remember, sound needs a medium to propagate through. So for all intents and purposes, we can think about the space as a vacuum, or the closest thing to a vacuum that we have, although in technicality it's not a vacuum. Does that answer your question? Awesome. So one way to investigate properties of the interstellar medium is to measure its effects on the starlight that passes through it. Astronomers observe that distant stars appear fainter than they should for their distances and luminosities, estimated from their spectral types. And this effect is called interstellar excitation. Distant stars also appear redder than they should for their spectral types. For example, some distant hot O stars actually look red rather than blue. This effect is called interstellar reddening, and is the result of interstellar excitation being stronger for short wavelength light than for long wavelength light. In fact, the interstellar medium is nearly transparent at near infrared wavelengths, allowing astronomers to look into and through interstellar clouds that are so dense they completely block our view at visual wavelengths. Another way astronomers detect material in interstellar medium is by observing interstellar absorption lines in the spectra of stars. So you can be sure that the interstellar absorption lines are not spectral lines of the stars themselves for several reasons. For example, some distant O stars show calcium and sodium lines, but those stars are too hot to form those lines in their own atmospheres. And those absorption lines must be produced instead by atoms located between the stars and Earth. So here is what we'll see. So in image A, we can see the interstellar reddening makes stars seen through a cloud of gas and dust look redder than they should because of shorter wavelength light is more easily scattered. Then in image B, no stars are detected at visual wavelengths through a dense cloud except near the edges. Then in image C, at longer wavelengths, near infrared wavelengths, many stars can be detected behind a cloud. And in image D, interstellar spectral absorption lines can be recognized because they are very narrow. So a good example is what we're trying to show here is, in visual wavelengths, you may see a patch of sky that's completely dark. You can't see any stars there. But that is because there's a gas cloud blocking visible light coming through. So if you look at infrared wavelengths, then you can see, but there's actually a lot of stars, and that means they are blocked by some sort of dust cloud. The widths of the interstellar lines also give away their origins. In the atmosphere of a star, the gas is so dense that atoms collide with each other and often, disturbing the electron energy levels, and so hard that atoms move rapidly, producing Doppler shifts. Both of those effects broaden or blur spectral lines from stellar atmospheres. In contrast, much of the interstellar gas is cold, and its density is very low, typically about 1 atom per cubic centimeter, although the density can be much higher in dense clouds. Even there, gas is 1 times 10 to the power 15 times less dense than the air you breathe. Because atoms in interstellar medium move slowly and collide only rarely, interstellar absorption lines are extremely narrow. So here we can see a broad stellar line, and here we can see a narrow stellar line. Spectroscopy tells you the abundances of elements in the interstellar medium. So about 70% of the mass of the interstellar gas is hydrogen, 28% is helium, and 2% is made of elements heavier than helium. The atoms are joined together to form molecules in the densest, coldest interstellar clouds, which are called molecular clouds. So astronomers have detected more than 150 different molecules in the interstellar medium. Almost all of the material in the interstellar medium is gas, but about 1% of the mass is made up of dust particles called interstellar dust. Studies of interstellar spectra reveal that the dust particles are composed of carbon, silicates, iron, ice, and organic compounds. Note that organic compounds are molecules based on multiple linked carbon atoms, which do not have to originate with living things. Details of interstellar excitation and reddening shows that the particles are almost all less than 1 micron in diameter. You can expect that if interstellar gas atoms are viewed against dark or cold background, rather than in front of the hot, bright background of stars' photosphere, those atoms can produce an emission spectrum. Interstellar emission lines, like absorption lines, allow astronomers to study that gas and dust between the stars. Cold neutral hydrogen floating in space produces a prominent emission line at a wavelength that can be detected with radio telescopes. This is due to the fact that electrons and protons have tiny magnetic fields because they are charged particles that are also spinning. So in this diagram, we can see protons and electrons spin and consequently have small magnetic fields. Because they have opposite electrical charges, they have opposite magnetic fields if they spin in the same direction. If they spin in opposite directions, their magnetic fields are parallel. As explained in the text, neutral hydrogen atoms flipping from the parallel to the anti-parallel state emit radio photons with a wavelength of 21 centimeters. So astronomers can use the resulting hydrogen in the 21 centimeter radio line to map the location of cold, low density gas in our galaxy. So when we look at our galaxy, and if we point our telescopes to the center of our own galaxy, we get this image. Here we can see a radio image. So you'll see there's a bright streak running here. What do you guys think is that? Any ideas? That is the disk of the Milky Way. So our center of our galaxy is over here, and everything, all majority of the stars lay in this disk. Does that make sense? Awesome. So when we say to take an infrared image of the galaxy, here we can see why would a majority of the stars lay in that disk. We will discuss that with galaxy evolution, how galaxies form. So you can think about it as a piece of clay, or even when you're making pizza. If you have it in a bowl and you start spinning that bowl around, due to the conservation of angular momentum, the ball will flatten into a disk. And that's the same thing that happens to our galaxy. That's why most of our stars are in this disk over here. Yes, you can see if infrared there's a few other stars that's not in disk. We call them halo stars, but that's something we will discuss in a later chapter. So here we can see all where the stars are located and the infrared that we can detect from them. But we can also look at optical. So in optical, we can see a bit of nebula, but we can't really see the center of the galaxy. If we take a look at X-rays, we can see even more details of our galaxy. So one thing is nebula. So what nebula is this? Does anyone recognize it? This is the Orion Nebula. So here is Orion's belt, and this is Orion's sword, and in the middle of the sword is the Great Orion Nebula. Another term I like to call the Orion Nebula is the interstellar nursery, because that is where stars are being formed and being born, which is very, very cool. Does anyone recognize this nebula? Oh, not the Helix Nebula, but this is the Crab Nebula, which is also very, very well studied, which is very beautiful. Do you guys recognize this nebula? Yes, that is the Horsehead Nebula, because it looks like a horse's head, and that is situated inside the Orion Nebula. So question, sir, can you explain the observable universe? Are we actually able to observe everything in it, and can what make the part of the universe observable? Because I think you once said that it's only theoretical and we aren't able to see exactly so far that what is the theory behind it, and why don't we know what is further? So one thing that we know is we can see the observable universe, so how far it has expanded. So remember, the universe expands almost at the speed of light, which is extremely, extremely fast. So the universe is getting bigger and bigger every day. But we don't know what it is expanding into, because we have no ways of how to detect it, how to measure it. So that is some of modern physics that we still try to determine, is what are we expanding into. Yes, we can observe everything in the universe. So where the universe is today and where it is expanding, we can see it, but we cannot detect what it is expanding into. I hope that answers your question. Okay, cool. And does anyone recognize this nebula? This is called the Cat's Eye Nebula, which is also very pretty to see through a telescope. So H2 regions, H2 is hydrogen, are clouds of gas ionized by ultraviolet radiation from nearby hot stars. They are often called emission nebula because the ionized hydrogen produces visible wavelength photons that make the regions glow with a characteristic pink color. If nearby stars are not hot enough to ionize the hydrogen in nebula, it may still be visible as a reflection nebula, produced when light is scattered by tiny dust particles mixed in with the gas. At visual wavelengths, dark nebula are visible where dense clouds of gas and dust are silhouetted against background regions filled with stars or bright nebula. So the key to understanding star formation is realizing the relation between young stars and the densest part of the interstellar medium. So in this image, we can see a giant molecular cloud began to collapse and form stars a few million years ago, including three massive star clusters visible in this image. Intense radiation and outflowing gas from the hottest, most luminous of those stars are exciting some of its gases to glow as an emission nebula and is eating into the remaining dark molecular cloud at a lower right. So this nebula is located in the Small Magellanica Cloud. So are you guys familiar with the Magellanica Clouds? So what we will learn about in a later chapter is the Magellanica Clouds are two smaller galaxies orbiting our own galaxy. So we can call them satellite galaxies. So you can only see them from very, very, very southern latitudes. So if you are in places in South Africa where the horizon is not obstructed, you can see it with your unaided eye. If you are down in the Western Cape or the Southern Cape, you can see it even better, and from Australia, even better. So it's one of the objects we can see with the unaided eye, but this nebula, NGC 346, are in the Small Magellanica Cloud. We have the Small Magellanica Cloud and the Large Magellanica Cloud. So I see a question. So if dying stars sometimes forms a nebula, are all nebulas remains of stars, or are some nebulas just interstellar gas? So it's actually both of them. So some stars, when they die, will form nebulas. And that stars that die that form the nebulas will cause a chain reaction that will cause new stars to be formed. And that nebula and interstellar dust are sometimes being pushed deeper into space. Then they come together and form new nebulas. But that's something we will also discuss in a bit of a later lecture. So, ladies and gentlemen, I think we will call this lecture for today. Next week, Monday in class, we will talk about star birth in molecular clouds. So if you have any more questions, I will remain active for another minute or two. Otherwise, have a great evening and enjoy the rest of your week. Yes, there are pressure in space. So there are a bit of pressure, especially in these nebulas and in other stars. And that is an important aspect that we will discuss in a later lecture. So question, sir, is it possible to know what's in a black hole? That is one of the things we do not know currently yet. So one thing is, we know our physics, we can break down the physics, understand what's happening until the event horizon of a black hole. So the event horizon is the point of no return. If you are outside of the event horizon, you still have enough speed to escape the gravitational pull. If you are inside the event horizon, nothing can escape it, not even light. That makes it extremely, extremely, extremely difficult to observe what's happening inside a black hole. And currently we do not know. That's why we are trying to figure out what's happening inside a black hole. Question, sir, are the slides enough to study for the semester test? It depends on your study method. So my slides are very detailed. So yes, you should be fine by just studying the slides. My personal study method is I make notes of the textbook itself, and then I use my notes and the lecture slides to study. But it all depends on your study method. Another question. Hi, sir. My weather forecast says that there is rain predicted for next week. Should we just wait until the sky clears to observe the moon? Yes. So you have to pick a week where there won't be any rain predicted. Another question. So what can we expect for the tests? Are there any practice problems? So yes, I will now, after this class, upload the lecture recording, and then I will also upload a mock paper that you can use for practice to see what kind of questions and how I will answer them. It's a pleasure. So if there's no further questions, I'm also going to log off. So have a wonderful evening, and I'll see you all next Monday.